Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed, and inspired. And I'm very willing to share my knowledge, especially topics in civil engineering for your benefit. The cylindrical pressure vessel with hemispherical end caps is made of steel. The vessel has a uniform thickness of 18 mm, an outer diameter of 200 mm. When the vessel is pressurized to 3.6 megapascals, determine the change in the overall length of the vessel. Use modulus of elasticity of 200 gigapascals and Poisson's ratio of 0.3 for steel. Neglect localized bending. So here's the given figure. The change in overall length of the vessel would be longitudinal strain times L1, which is 600 mm, because this is radius, so plus strain in this direction for spear, which is circumferential in the direction of diameter times internal diameter. So delta L is delta L1 plus delta D, change in the internal diameter also. So sigma sub c is PDI over 2T. We can make use of this because internal radius divided by thickness is definitely greater than 10, greater than equal to 10 in this case. So internal diameter is 400 mm minus 2 times thickness of 18. So internal diameter is 364 mm. Internal radius therefore is 182 divided by 18, so that's more than 10. So that's why we can use this formula here. So substitute sigma sub c equals pressure 3.6 megapascals times 364 mm over 2 times 18. So the circumferential stress is 36.4 megapascals. Circumferential stress is one half of the longitudinal stress, or longitudinal stress is one half of the circumferential stress. Therefore, longitudinal stress is 36.4 over 2, because the formula for longitudinal stress is PDI over 40. So it is one half of the circumferential stress. So longitudinal stress is 18.2 megapascals. So we can now compute the longitudinal strain, which is 1 over E, quantity longitudinal stress minus Poisson's ratio times stress perpendicular to the longitudinal direction, which is the circumferential stress. Longitudinal strain is 1 over E, quantity longitudinal stress minus Poisson's ratio, circumferential stress or stress perpendicular to the longitudinal stress, or stress in the direction perpendicular to the longitudinal direction. So substitute longitudinal strain is 1 over 200,000 times quantity 18.2 minus 0.3 of 36.4. Longitudinal strain is equal to 3.64 times 10 to the negative 5. So strain in the direction of diameter is 1 over 8 times stress in tangential to the diameter minus Poisson's ratio times stress perpendicular to the diameter or radius, which is the longitudinal stress supposedly. The longitudinal stress for spherical tank is also the circumferential stress. Remember, the formula is PD over 40, PDI over 40, and it's the same in any direction for spherical tank. Therefore, sigma is equal to circumferential stress equal to tangential stress for spherical tanks. So since sigma L, formula for sigma L for cylindrical tank is the same as that of spherical tank, PDI over 40, then we don't need to compute the circumferential stress or sigma for spherical vessel. It is already 18.2 megapascals. So factor out sigma, which is 18.2 over 200,000, then we have 1 minus Poisson's ratio of 0.3, because sigma is equal to sigma L and sigma L is equal to sigma C for spherical tank, which is 18.2, or longitudinal stress for cylindrical tank. So the strain in the direction of diameter is equal to 6.370 times 10 to the negative 5. So therefore, the change in overall length is strain longitudinally times L1, which is 600 mm, plus strain along the diameter in the direction of the diameter times di. So delta L is 3.64 times 10 to the negative 5 times 600 mm plus 6.37 times 10 to the negative 5. Internal diameter is 364. So the change in the overall length of the vessel is equal to 0.04503 mm. The thin-walled pressure vessel has an elliptical cross-section with the dimension shown in the figure. Assuming that A is greater than B and that the wall thickness T is constant, derive the expression for the maximum and minimum circumferential stresses in the vessel caused by an internal pressure P. So here is the given figure. Remember the principle that for maximum circumferential stress, sectioning must be done in such a way that the projected area of the pressure would be maximum also. Since A is greater than B, for maximum circumferential stress, the tank should be sectioned as follows. Then we consider the lower portion of this section, and we consider a strip of length S as shown in the figure. So that dimension is A, internal diameter of the ellipse. So the thickness is T, and this is S. Then this projected area, which is rectangular, is subjected to pressure, and the force would be pressure times area of the rectangle, which is A times S. And that should be resisted by the tensile stress or in the walls, normal to the wall. And that is sigma sub C max, circumferential stress, times area of the rectangular wall, which is thickness times S. And there are two walls. So summation forces vertical equals 0. PAS equals to sigma C max times TS times 2. So cancel out S. So sigma C max is equal to PA over 2T. In a similar fashion, so we section the tank in this manner, and the dimension would be, and summation forces horizontal, then the result would be sigma C minimum would be PB over 2T. So it's not shown anymore because the free body diagram would be the same, except that the dimension here is replaced by B, and sectioning should be vertical in that sense. So that's it. I hope that you were able to follow the explanation and the solutions.